We'll finish up with bipartite graphs, at least for the current time, talking about a complete bipartite graph. A complete bipartite graph with bipartition V1, V2, those are the two sets, with one of them having an M and one having an N vertices, is labeled as KMN, complete with two subscripts now, M for one of the vertex sets and for the other, the bipartition. It's complete bipartite if it contains every edge it possibly could. In other words, for every vertex in V1 and every vertex in V2, there is an edge. So let me draw a couple of cases here. So K2 is actually one we've already drawn because this is actually the same as C4. It turns out it's just a different way to sketch C4. So this is a graph that looks like this that we saw in one of the previous videos. So that's K2. This is the vertex at V1 and the vertex at V2. K2, 3, and I'll often write the smaller number first, although they're really not different graphs. They just may look different because of what we put on top and what we put on the bottom. K2, 3 has V1 has two things, and V3 has three. V2 has three. And so each vertex in V1 must connect each vertex in V2. But of course, there's no interconnections of things in V1 or things in V2. So that's K2, 3. And you can see how it goes from there. I think that's enough to get an idea of how that works out. So we'll come back to bipartite graphs and look at an example with them in an interesting theoretical result in a future video. But for now, what I'm going to do is turn now to a first theoretical result in graph theory, our first theorem. And as I do that, I'm going to define the notion of even vertex or odd vertex in terms of whether the degree of the vertex is even or odd. So if the degree is even, the vertex is an even vertex. We'll just call it that way for brevity. So the theorem that plays off on this says that in a graph with vertex V and edge set E, the sum of the degrees of the vertices, if you add up all the degrees of the vertices, you get twice the number of edges. That symbol there, remember, means the number of things in E, so that's the number of edges. So twice the number of edges, you might want to write it that, twice the number of edges is the sum of the degrees in V. And so let's look at an example or two and see why this is happening this way. So off to the side here, I'll draw a little example, maybe something that looks like this. And I'm going to maybe make it a little bit more complicated, make a couple of threes there. Okay. A, B, C, D, E. And let me go ahead and label the edges as well. That's an A up there. It looks crazy, but let's call this edge. Let's use alpha, and let's call that one beta, and that one gamma, and this one delta, and this one epsilon, and this one I don't know. Let's call it iota. Iota is like an I. Okay. So like so. Now we're not going to go through and do all of those, I don't think. But what I'd like to do is write down a list of the vertices. So I'll write vertex here, and we'll do A, B, C, and D, and E. And over here we'll write the degree. And so the degree of A is 1, 2, 3. The degree of B is 1. The degree of C is 3, the degree of D is 2, and the degree of E is 3. Okay, and the sum of the degrees is 6, 9, 12, right? So here's the thing that I want to look at. Let's look at alpha here. So alpha is counted once here and counted once here for A and B. So alpha is counted here and alpha is counted there. beta is counted with C and D. So beta contributes 1 to that 3, and beta contributes 1 to that 2 on D. And then gamma is counted once for C and once for A. So it's counted for A and it's counted for C. So gamma counts 1 towards that 3 here, and gamma counts 1 towards this 3 here. And then delta likewise counts 1 towards D and 1 towards E. Epsilon counts 1 towards A, right? Because it's attached at A, and it counts 1 towards E. And then iota counts 1 towards E and C each. There's C and there's E. So each edge is counted here twice, and that's why this is 2 times 6, where the number of edges is 6. 1, 2, 3, 4, 5, 6. So the theorem works in general that way. The proof would say as follows. Since each edge contributes to the total sum of degrees, twice the number of edges will be the sum of the degrees. That's all there is to it. Now, this also points out why we wanted to let the degree of a loop be 2, because this edge right here, we ended up with iota. I don't know. I guess I can't remember what's next in Greek. I think it's eta. Looks like a elongated N. This edge also counts 2 to the degrees because we've defined it that way, that this contributes 2 to the degree of B. Yeah, that's why we did that. So it's still true there now. In this case here, we kicked up B to 3, and so eta counts twice here. And we get 14, which is 2 times 7 appropriately. So one thing that comes out of this is that every graph has an even number of odd vertices. Why is that true? Well, the sum of the degrees has to be even. So if you sum the even degrees, V even, plus the sum of the degrees of, I'll call them the U's, where U is odd, then this is even because each of these is even. So this is even. And so this has to be even, must be even. Why? Because the total is 2 times the number of edges. That's even, right? So the total, adding up all the degrees, is even. But if you just add up the degrees of the even vertices, that's obviously even. So this must be even. But the sum of an odd number of odd integers is odd. So the number of odd vertices must be even. Now, that's an interesting little corollary. It tells us something about what sort of degrees are possible in a graph. By the way, the graph here doesn't have to be simple in either of the theorem or the corollary. It can be a multigraph. And it doesn't have to be what we'll later define formally as connected. It could be something like this. It could have 2 pieces to it like so. It's still true. We're going to make use of this to talk about what kinds of degrees lists can actually occur for a graph. We'll call that a degree sequence. So the degree sequence of a graph is the list of the degrees of the vertices, all of them, even if there's duplication of numbers. A list of the degrees of the vertices of the graph And we'll just always do it in descending order. Okay. A finite list of non-negative integers in descending order might be a degree sequence for a graph, or it might not. We say it is graphic if it is the degree sequence of a simple graph, So here I'm insisting this one's a simple graph. Okay, so a graphic sequence is the degree sequence of some simple graph. So let's figure out in this example which of the following are graphic sequences. Let's see, could that be the degree sequence of a simple graph? I hope that one's pretty quick. Pause if you want to think about it, maybe look back. Right, that cannot be because it has an odd number of odd vertices. So this first one here, 1 is no. Odd number of odd vertices. To make it a sentence, it has an odd number. I know how to spell odd. O-D-D. It has an odd number of odd vertices. Okay. How about 2? 2 has 3, 3, 3, 1. So it has to have 3 vertices of degree 3 and 1 of degree 1. So in this case here, I'm going to just think about it a little bit more. So let's call that. There's obviously 4 vertices if we were to do this, A, B, C, and D. And rather than just trying to sketch this and say, I can't do it, I want to analyze it and see what is going on with it. So that means that because there are 4 vertices and A has degree 3, A must connect to each of the other 2. Okay? So that would mean that already B, C, and D have to have a degree of 1 at least. And then B has to connect, well, B's already connected A, but it has to connect to all of the other 3. So it has to connect here and here. And that would mean that C and D must have degree 2 at least. Oh, already we've discovered that that's not possible since the answer is no, since 3 vertices connect to all of the other 3 vertices. So A connects to all of B, C, D, B connects to all of A, C, D, etc. Each vertex must have degree 3 or more, but one vertex has degree 1. So that's impossible. So then 3 is 4, 4, 3, 3, 2 a graphic sequence. And before we do that, let me just go back real quickly. Notice in this last case here, 3, 3, 3, 1 has an even number of odd vertices, but it's still not graphic, right? So that is not enough to say it's graphic, to have an even number of odd vertices. Okay, so let's go ahead and look at this one then. Here, 4, 4, 3, 3, 2, could that possibly work out? Let's see, there are 5 vertices there that are represented, right? A, B, C, D, E. A, B, it's a little hard to read that here. So this would be A, B, C, D, and E, and their degrees right there. So A and B have to connect to each of the other 4. So if we were to try to do this, and it doesn't hurt to sketch it to try it, A and B, like so, have to connect to each of the other 4. So let me draw these right here. So A would have to connect to each of the other 4. B is already connected to A, would have to connect to the others here, C, D, E. So far so good, but C and D would have to connect to another one each. Oh, they can connect to each other. So it is graphic. It is graphic. It being the sequence. 4, 4, 3, 3, 2 as a graphic sequence. Okay,